Welcome to part 3 of our journey in learning more about ChatGPT and related technologies. So this one we're going to dive in a little bit under the covers, understand how this works, which is probably a little unfair because we understand what it does, not necessarily how it works. But more about that as we go through this presentation. So what does ChatGPT do? I'll start off really slow. Then what I'll do is I'll start layering on levels of understanding. So essentially what it does is it builds a response to your prompt word by word. So first it generates the first word of the response, then the second word, then the third word, and so on. Each time it generates a word, it considers a few things: your prompt, the response so far, the larger context of the conversation you've had thus far, all the content it was trained on, which is quite significant. It also takes one more thing into context, and that is some, you could call them meta settings. These things that you can override if you want, things like temperature. Remember, we dealt with the temperature parameter. So it takes all of those into consideration when it tries to figure out what that next word should be. The training set is massive. So there's a high degree of likelihood it's been trained on many pieces of content that pertain to what you're prompting it about. But you could kind of visualize it like here. The best thing about AI is the ability to, what's the next word? Well, there's different likelihoods that each of those are the next word, and it chooses one of them. So that's at a high level what it does. So in essence, it determines the word that is most likely to come next, given all that information. And here's a little interesting visualization. I'm actually going to switch to it for a moment. It's a little tool. And the link to this page is on that slide. And what this person has done is he's created a little tool and he's entered a block of text. So I built this little tool to help me understand what it's like to be in an autoregressive language model. For any given passage of text, it augments the original text and highlights the annotations that tell me how surprising each token is to the model. So remember I said it doesn't always pick the highest probability word. Sometimes it chooses other words based on a number of factors. And so he goes on here. For example, if I start counting to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's the text where you can see the probability of the word that it had anticipated if you're to run the model. And so, for instance, it didn't, it wouldn't have predicted the number 1 or the word 1. It wouldn't have predicted the word 2, but then it would have predicted the word 3 and so on as it went along. And it's also interesting if you look at the alternatives it was considering. So here it, at that time when it was going through, would have predicted the word 10 with 19.467% probability. It would have predicted a return, so no number at all, with 14.349% probability. It would have predicted the number 10 with 8.986% probability, and so on. This tool is kind of interesting. So you could replace this text with your own text and run it. But one thing he mentions here is one striking observation from this visualization is that these models are particularly good at noticing and catching onto repetition. And so what he comes up with is he comes up with a sentence with some words that are really unexpected. The first time I write the sentence, the model is quite confused about the token what token is about to come next, especially if I throw weird words like pumpkin, clown, tweets, alpha, teddy bear. And so you can see that down here. It is like, yeah, pumpkin. It wasn't one I was considering. I wasn't considering clown. I wasn't considering tweets. Wasn't considering alpha. But then you can say, but the second time, it expects almost every word that appears. And so you repeat that sentence, and as you can see down here, all green. So this is an interesting tool for just playing around and having a look. If you were to, reapply these types of models to some text to show how surprising a particular word may or may not have been. So a curiosity, so to speak. Okay, so what is a large language model? There are several large language models. There's GPT-4 from OpenAI. There's Llama from Meta. There's Palm 2 from Google. I think it was John sent me a message during the week. There's Claude from Anthropic. So there are lots of these large language models out there. There are a bunch of open source ones as well. Now, what I want to do is just want to reinforce that these are not conventional software with explicit step-by-step instructions like maybe many of us have encountered before. They're neural networks that are trained using billions of words of ordinary language. So during training, we're going to get into this a bit deeper soon, the model learns the statistical relationship between the words. It doesn't explicitly store grammar rules. It implicitly picks them up. It's not programmed to write stories or poems. It learns how to do so during training. So just to reinforce this, let me jump out again. I am going to go into the code repository for one of these systems. And so in this code repository, it's a Python implementation of what we're going to walk through during this session. And so if I go in here, and if I go in to the actual transformer, which we're going to walk through, here's the code to run this. So here's the constants. It's only a few constants here. Here's the code to implement the layers. It's only 42 lines. Here's the code to implement the models. It's 198 lines. Here's the code to implement the modules. It's only 25 lines. The optimization, it's only 40 lines. The sublayers, 82 lines. And the translator, because this particular transformer is a translator, 114 lines. So it's not a lot of code to create a very complex system like this. So I just want to reinforce something that is mentioned here. So neural language models are not long programs. You could scroll through the code in a few seconds. They consist mainly of instructions to add and multiply enormous tables of numbers. The numbers, in turn, consist of painstakingly learned parameters or weights, roughly analogous to the strengths of synapses between neurons in the brains and activations, roughly analogous to the dynamic activity levels in those neurons. So this guy, Blaze, Google Research, quite a prominent person, we actually came across him last week as well, mentioned that real brains are vastly more complex than these simplified model neurons, but perhaps in the same way as a bird's wing is vastly more complex than the wing of the Wright brothers' first plane. So the code to implement these systems is pretty straightforward and pretty simple. All of the smarts are in the training that derives the weights in the neural network. Okay. So there was a 2017 paper, so quite recent, that really unlocked these systems and is the basis for most of these impressive large language models that are out there. The paper is called Attention is All You Need. It comes from a bunch of people across Google, University of Toronto. It introduced what's called the transformer architecture. So that's where we're going to spend this session, in the transformer architecture. A few things that I'll just call out why this was pretty groundbreaking. One was the way in which it can take advantage of parallel execution. It takes advantage of parallel execution in ways that a lot of systems like this have not been able to in the past. And because of that, it allowed for certain breakthroughs in scale. Another reason is because it takes more words into context. So it takes, I believe it's a context of 2048 tokens. So let's call it 2048 words. So that's the window of words it's looking at any one time. It recognizes that the relationship between words is important. These guys aren't the first to recognize that. This had been floating around for quite some time in the research world, but they did take it to the next level. So one way to think of this is you can have a dictionary and you can understand the meaning of a word. However, a lot of words have multiple meanings, and that meaning depends on the context. It depends on the words around it. And so that's why we're saying, part of the reason we're saying that the relationship between words is important. They also said that paying attention to important words is the key. So, recognize that the words used in the context is important. Then identifying which of those are the key ones that you want to focus on is actually part of the big breakthrough. This paper has been cited more than 80,000 times by other researchers. So that's a mind-boggling number. Yep.
When you had that graph that showed how fast things were progressing,
yep,
you sort of said it was because we started using faster GPUs or something like that. Is it also in part because of this paper, because the software changed because of this?
Yep. So the question is, in a previous session, I showed a chart showing the scaling of these training systems and the roles that GPUs played in that, the advances in hardware. The question was, is this paper also a significant factor in that? And the answer is yes. In fact, so the GPUs predate this, but this paper really brought about that step change because we did have the GPUs that could implement it. Okay, this is the transformer architecture. By the end of today's session, we should have a better understanding of it. So let's start stepping through parts of it. So what I'm going to do is I'm going to deal around the edges to begin before I start going into the heart of it. So let's start working around the edges. First thing we're going to look at is down the bottom left corner, where the words come in. Okay, it's called the input embedding. Basically, we convert the words into something that the system can work with. The system can't work with words. Neural networks work with numbers. So let's convert the words into numbers. Okay, so here's the first thing that actually happens. The large language model, it breaks the content. So let's say that the content that's coming into the large language model is many words mapped to one token, comma, but some don't, colon, indivisible, period, and so on. Let's say that that's the language coming in. Now, it converts that language into what it calls tokens. Now, a token can be a character, a symbol, a word, a part of a word. There's a general rule of thumb that that 75 words equals about 100 tokens. So here we've got some color coding to indicate the tokens. And so many is a token, so that's a word. Words with a space before it is a token. Map with a space before it is a token. And so you can see that for the most part, these words are mapping to tokens, but some don't. So we're at the word don't. That's 2 tokens. So in some cases, what happens is, if there is a part of a word, if there's a word that's, if there's a part of a word that's used frequently, sometimes it can be its own token. Now, the techniques for choosing what's a token and not are not always the same from system to system, and they have evolved over time. Don't read too much into it. Essentially, this is just, hey, how can the system most efficiently deal with the words coming in? And in some cases, particularly for big, long words, it's not by treating it as one word, by trying to break it up into commonly occurring component parts. So we've got these words. They're converted into tokens. Those tokens are in turn converted into token identifiers. So basically a number that represents that token. Now that token identifier essentially just points at something else called an embedding. So we've got a token identifier. You could just kind of, think of it as an index into a big long list of embeddings, each of which represents a token. And these embeddings are actually big vectors that represent that word, represent the meaning of that word. Now, why are we working with vectors to represent the meaning of a word? Well, we want to work with numbers because we want to use a neural network. And for that, we need to be able to do some math in the neural network. And it so happens that certain types of math work particularly well for representing the relationships between tokens when they're in vector form. So I'm gonna really dive into this now for a few minutes because it's quite important. But before I do, I'm going to jump back out, and I'm going to go to the link that's on this slide. And this is another useful tool if you want to play around with this tokenization to get a better feel for it. And so you can see that the tokenization is different from GPT-3 to GPT 3.5 and GPT-4. But here is that example text I showed you. And that example text turned into 57 tokens, as I showed you here. And if I want, I can switch here to the token IDs, and I can see these IDs for the tokens. Now, if I want, I can go somewhere else to show the vectors. I'll do that in a moment. But anyway, go here and you can play around and you can enter different text in here, and you can see how it gets converted to tokens. So we got words. Those are turned into token IDs. The token IDs are essentially placeholders for the embeddings, these big matrices with lots of numbers in them. And that's, of course, assuming that the word is represented by a single token. Okay, so here is, for instance, a vector representation of cat from a system. And you can see here that there are lots of numbers in this vector representation. Now, we're going to go and we're going to visit this webpage in a moment. Again, you can click on the link here to go through and start playing with this yourselves to get a good feel for it. But one thing I'll point out is that this vector representation of cat, it's for a 300-dimensional vector. With ChatGPT, we're dealing with 12,288 dimensional vectors to represent a word. It's a lot of numbers. So you might be wondering, why do we need so many numbers to represent a word? Okay, well, let's proceed and learn a little bit about why that is. So these numbers, they essentially capture the meaning of the word. And we'll start to understand why that is as we go on. Yeah.
Can I ask a question about back up a little bit, because I want to ask you where some of these things come from.
Yeah.
They come from the automatic training. So
yeah, that's a great question. So Harry asked, where do these numbers come from? Do they come from the training? So the answer there is yes. Essentially what happens is we're going to get deeper into this architecture, this transformer architecture in a few moments. That transformer architecture is used both to train the system and at what's called inference time to respond to prompts. It operates a little bit differently when training the system than it does at inference time. But essentially what happens is when we start a training run, all of these values are quite random. Over the course of training, these numbers get tuned into their final state. We're using neural networks. We're using content where we know what word comes next, but we're continually feeding this through and masking out what comes next to see what the system would predict. Then at the other end, we're seeing the prediction and we're seeing what actually is in the content. And then we're calculating what's called a loss function, where we're identifying how far off we were. And then we're going back through the neural network and we're back propagating that difference to make tiny little adjustments all through the system. And we're doing that billions of times. And so over time, what's happening is these numbers are getting more and more tuned to the point where right now they're doing a pretty good job of, creating intelligible text that is on point. So that's the long answer. So the short answer is yes. These embeddings come from the training of the system. Okay, I am going to go over to another page that's linked to from the presentation. And again, the reason I'm including this is if you want to go in and start playing around and just get a better feel for what's happening. This is a page where they have created these embeddings, these vectors, for a number of different training sets. And so you can go in and you can look for a word in the training set, and you can see its relationship to other words in the training set. You can see a plot of the vector. You can actually see the raw vector numbers. And so you can do this for other models as well. So the British National Corpus, Google News Corpus, English Google Word Corpus. and it looks like a Norwegian corpus. But anyway, I just want to make you aware of this, and you can search for other words, or you can click through and see about their relationships to one another. We're going to get a little bit deeper here now into this for a few moments. So I mentioned earlier in passing that one of the benefits of these vectors is we can do certain types of math on them, and that they preserve relationships between words. Okay, what do I mean by that? Okay, this is a very simple way to convey that. Let's just imagine that we're dealing with a two-dimensional space. So conceptually, we found over decades, when working with these types of systems and making them better over time, one of the bigger breakthroughs was made by Google in, I believe, around 2012, when they used vectors like this to represent the words on Google News. And when they did it at a scale that hadn't been done before, they started to discover that they could do math on the vector relationships of these words, and that math corresponded to the relationships between the meanings of the words. So for instance, if they took the word big and looked at the difference between the word big and bigger, and then applied that to small, they would arrive at the word smallest if they just did the math on the respective vectors. But this type of relationship also applied to, for instance, countries and the language spoken there, countries and their capital city, countries and the name of the term we use for the people from that country. So it was really interesting. All these relationships between words were captured quite well in these vectors. But another thing to note is, because these vectors are coming from human language, they reflect certain biases. So for instance, if you do the math on doctor minus man plus woman, it actually doesn't come back to doctor, it comes to nurse. So there are some biases that exist there. Now, again, let's jump out here, because there's another awesome resource that we can use to play around with this. It's from the same website as the last one. And if we go here and actually, let's start to change some of these. Let's say that this is king, and let's say we have man, and let's say we change this to queen. And now let's say we calculate, what's it going to give us? Oh, sorry, calculate on this side. Oh, it lost my things. Okay, let's try it again. So I think I had king, but we could also play around with this and do other ones. And what it's doing is it's going and getting the respective vectors, and let's calculate now. Did I click on that? Oh, here we go. Finally. I think it was selecting the button rather than clicking on it. And so it says, okay, the most likely is woman. And that's using the English, a training set from English Wikipedia. I could change it to another training set and see. So woman didn't come far ahead of men there. So.
But woman was represented twice in that last set.
Yes. So let me go back to that and I'll look to see what that was. But here, and if I look at the Google News training corpus, woman again comes out, girl is second. So this corpus, maybe it's a bit more extensive, but also the content of it probably does a better job of leaning towards coming out with better answers here. So let me actually go back to English Wikipedia and have a look at why woman might have been there twice. Oh, here we go. Yeah, so it says woman the noun and woman the verb and woman the proper noun. I'm guessing there must be some usage of woman as a verb. Yeah, I'm not sure about that. Okay, but anyway, interesting tool. You can start to play with the vector representations, doing the math and seeing about some of these relationships, maybe putting in countries and their capital cities or whatever. So now one thing to remember is that this 2D representation was made to, keep things nice and simple. But what we're dealing with is we're dealing with a 12,288 dimensional space. So we're dealing with just this huge space that's difficult to wrap your head around. Actually, I think I've got another one, which is, so this is another one, which is a visualization of the space. Again, it's a smaller one. There's a 200 dimension vector. But what we can do here is, yeah, let's have a. Makes sense to me. Okay. Let me refresh this. Okay, I'm going to search for the word bank, which can have multiple meanings. I'm going to click on bank here.
Question. What are the axes?
So this is, so this is a way where they're trying to make it consumable. So it's not really a true representation of 200 dimensions. What they're trying to do is they've got an x-axis, a y-axis, and then what they're doing is they're, I believe, turning the other dimensions into revolving. It's almost like a third dimension, but they're trying to represent this space here. Bottom line, actually, I don't have a good answer to that. A good, clear answer.
If you look, there's an axis there, a vertical axis, and there's something out like 7 o'clock, and then now something about 3 o'clock. So it looks like there's 3 dimensions trying to be represented in a 2-dimensional space, for sure.
It's actually trying to represent a 200-dimensional space.
Understood.
Yeah, but
question here about the math behind this.
Yeah.
Is this using what we learned way back in the dark ages, this matrix algebra?
Yes.
To tell these vectors,
Correct.
find the vectors?
Correct.
Okay, so that's how we do it.
It is. And so there's some real interesting aspects to that as well, which we'll get into in a little bit, where essentially these vectors represented by matrices, if you have words that are close together, they tend to have similar meanings in these spaces.
Excuse me, and they use probability theory to try to get the relationship between them and to get the intensity, let's call it, of the relationships. Is that true too?
That's a really good question. And sorry, the question is, are we using some sort of probability theory to get the relationships between the words? That's going to become clear soon. There's a technique that was part of that paper that's a breakthrough that really focuses on the relationship between words. So that's coming very soon. So one thing that I wanted to point out here is, so this space is actually quite big, and the words are actually a reasonable distance from one another. So the ability, it's not like the words are all on top of one another. There are 50,000 plus words in the vocabulary of GPT, ChatGPT. And when plotted onto a 12,000 plus dimensional space, there's actually quite a degree of space around these words, and the math that we're going to do operates quite well on them as a result. And so if you follow this around, you'll see a lot of relationships with words in a financial sense, but you'll also see here and there river bank related terms popping in and out. But anyway, another fun visualization to go and explore and figure out. Okay, so we've dealt now with content getting into the system so we can do something with it. One of the key considerations here that we need to take into account is, because this system is going to act in parallel on each word, so each word goes in at the same time, we actually need a way to capture word position. Because if we don't capture the word position, then essentially we've just got these words going through and we don't have much else to rely on other than the meaning of the word, which could be ambiguous. So we need a way to capture the position. And what we need to do is we need a way to capture the position in absolute terms, where the word occurred in the sentence, as well as in relative terms to other words. And so what this architecture uses is it uses a periodically varying function. What it does is it actually alternates sine and cosine formulae. But it also wanted to use a function that doesn't make a huge change to the meaning of the word, because we're going to have to incorporate this positional information into the embedding, into the vector that represents the word. So we do want to be able to incorporate positional information, but we don't want that positional information to be so heavy as to outweigh the numbers that are representing the meaning. And so, as I mentioned, there are a couple of formula that are here where it says positional encoding on the right in the middle. This is almost accurate. There are actually exceptions for a couple of values, but at the beginning, slightly different formula. But these are the formula, and they're dependent on the size of the model. So there is these numbers will be a little bit different depending on which particular system you're using. The other thing to note is that these numbers are computed in advance. And so essentially it's just like a table lookup for these specific values. But these positional encodings are added into the embeddings. It's actually an addition operation that adds them in. Okay, so we've talked about getting information in now. We haven't talked about anything about what happens to it. Let's talk about the information that comes out, and then we'll deal with what happens in the middle. So this architecture, what it does is it outputs a vector. You might imagine that, given we're dealing in vectors here. And then we've got a step here, the linear layer. And what it does is it projects that vector onto a much larger vector. For ChatGPT, this vector has more than 50,000 scores that come out. One score for each word in its vocabulary. And then there's a function that essentially turns that score into a probability. All the probabilities will be positive. All of them together will add up to 1. So in other words, the output's a vector indicating a probability score for each possible word that there could be. So remember, what we're trying to do is we're just trying to come out with word by word generating output. So we're just trying to generate the next word. That's all. So all we want to do is we want a word to come out the other end of this. So what comes out is a big vector with all the possible words. I'm taking some liberties here. And a probability score for each possible word. And then what happens is one of the higher probability words is chosen. Notice I didn't say that the highest probability word is chosen. There are things like, so sometimes it might not choose the highest probability word. Sometimes the temperature setting might direct it to not choose the highest probability word if you want to generate more colorful output. But also I'm oversimplifying here a little. It takes advantage of something called beam search, where it actually looks at combinations of words. But in essence, just think of it as, yeah, you know what? Out the other end of this is going to come an analysis of every possible word and the probability of that word being next. And then it chooses one of those words. So, summary thus far. We supply an input sentence. Let's say the input is the sky is. So the input sequence is translated into tokens and then token IDs and finally embedding vectors. For every word, the transformer outputs a vector indicating the probability that a particular word should appear next. And then the system chooses one of those, and maybe it'll say the sky is blue. Okay, we've dealt with information coming in. We've dealt with information coming out. Let's deal with the middle. And so you might think that, hey, you know, we're just getting to the fun part now. But remember, the fact that the words are represented as vectors is key in all of this. The fact that these vector relationships actually do capture some semantic meaning in the words is also key in all of this. And for other reasons, we're going to see there are other properties of the fact that we're representing as vectors that are going to be very important as we go forward.
Is this a good place to pause and take some questions, or do you want to go further?
Sure, let's pause here.
All right, because I saw Mike Alexander had his hand up, and he's been very patient, and I appreciate that. So
Yeah,
Mike,
I feel, yeah, my questions are very similar to a lot of these that are in the chat, but my question is what determined the dimensionality of this?
Yes, good question. What determined the dimensionality? Yeah. So first of all, experimentation, and then empirical evidence that certain dimensionality work best is a factor, but it's not as simple as that. The dimensionality chosen has consequences for the dimensionality of other parts of the system as you're going through it, other parts of the architecture. So it's not just as simple as saying, hey, we experimented with a few different dimensionalities and we chose this. It's quite complex in some of the relationships that the dimensionality chosen will have on subsequent parts of the architecture. So not only were there experiments run with different dimension vectors, but also there were experiments run with different numbers in different parts of the system, not necessarily dimensionality, but different numbers of layers, different context sizes, and so on. But yes, for the most part, the short answer is experimentation was run to try and optimize the dimensionality for the quality of output. So in other words, make it as big as possible, but also take into account other parts of the system and making sure it all works together.
Is that the answer to Carl's question, why 12,288 was chosen?
Correct.
Yeah. Mark was asking, I wonder why the numbers in the vector have so many digits in them. Does this quote unquote precision increase with training?
Yeah, so that's a good question. So I think everybody heard the question, but this is essentially, hey, why do the numbers in the vectors have so many digits? And the answer is yes. Essentially, it's around optimizing the precision of the system.
So the number of dimensions was just a choice of how much they could handle with some amount of computing power. And that's probably, I would guess that was part of the training issue, was that they saw what was optimized for the technical environment.
Yeah, so yes, the dimensions were chosen to try and, optimize, get as much compute, as much scale in there as possible, as be able to differentiate between words in the vector space, but also, there are relationships between this number and other parts of the system. So that was a factor that needs to be taken into consideration as well. A lot of the vector dimensions through the system essentially work towards, having various operations performed on them and coming out with certain dimensional vectors as well. So, there's a bunch of relationships here, but yeah, essentially we're just trying to optimize. There's nothing magical about a particular number.
Good. Barry is asking, in otter speech to text, sometimes Otter will go back and change an earlier word. But GPT locks in a word once chosen, never going back to alter an earlier word. Would that practice ever become an advance in these narrative language models?
Yeah. So there are actually some types of large language models that are bidirectional, but this is not one of those. You are correct in stating that it essentially moves in one direction only. And it just outputs. It does not go back to revisit individual words chosen in its output.
And then Carl asks, the sky is blue. Blue is a good choice after the sky is, but is by itself doesn't particularly map to blue. So the whole of the sentence so far determines whatever Carl was saying. Whoops, there we go. The next determines the probability for the next word, correct? How long a sequence is considered?
Yeah, so the sequence that's considered is up to 2,048 tokens. If there are fewer, like there are here, essentially a lot of those tokens just get padded out, so not used. But yeah, so the maximum context is 2,048.
So asking that differently, the first token in the sentence has no ancestors, and therefore it's a swag.
Yep, that is correct. There are special tokens as well for start of a sentence and end of a sentence.
Oh, so they have, this is the start of a sentence as a token associated with it.
Yeah, just so the system knows when to start and stop its operation. But yes, so when it's starting off, it's probably going to choose a word that you might commonly start a sentence with. But yes. And so it's interesting, one thing you can do too is you can put that text into some of the tools we show earlier, and you can see the probabilities of other words other than blue. So you can see what it might have chosen. And one thing to remember is the temperature setting does have an impact too. You won't be able to set the temperature setting for some of those tools that I give you links to, but they're interesting nonetheless to see what the alternative words the system was considering.
Would you just do me a favor and just review what temperature means in 25 words or less?
Yeah. So the temperature setting is something that you can specify when you're issuing a prompt to indicate to ChatGPT how on point you want it to be or how creative you want it to be. And if you say, hey, I want you to be like really on point, it'll come back with the sky is blue. But if you go to the other end of the spectrum, it will produce a flowery sentence or two about, cerulean and all various, it'll be quite poetic and creative.
Where does the temperature come in?
Yeah, so the temperature comes in when ChatGPT is choosing its words. So if you set it to be a temperature where you want it to be more creative, then it's going to look not necessarily at the highest probability word, but maybe one of the words further down the list, and then do the same the next time around and the next time around. And so you'll end up with a kind of a flowery textual description.
Maybe at the end of this, we have a few minutes. We can take a simple example and play with the temperature.
Yeah.
And see what that does, because I think that's something that's interesting that a lot of people don't understand how to use.
Absolutely.
You don't need GPT-4 to set the temperature, because I haven't seen it.
So if you look at, I believe it was the part 1 of this, I give some examples of how to specify the temperature when you issue a prompt. But no, you can use it with GPT 3.5 as well.
I thought so. Good. All right. Thanks, everybody, for your patience.
Okay. So now we're going to get in to the meat of the system.
We're 10:55. You're okay on time?
I'm okay on time.
Good.
Okay, we've represented words as embedding vectors. Now what we're going to do is we're going to learn more about the words and how they relate to one another. And we're going to use something called attention. There are 3 attention layers in this. Each of them operates a little bit differently, but for now, I'm just going to deal with this in quite general terms, just to convey what attention is all about. And basically, it's all about a bunch of math, but it's a bunch of math with a means to an end. So each of these attention parts of the system, they have what are known as 96 attention heads. So we've got 96 of these that are going to do something. Now, if you look here, you can see little NX. NX are the number of layers. We've actually got 96 layers as well. These layers can be visualized as a stack, one after another. Layer 1, layer 2, layer 3, layer 4. So we've got 96 of these, and within each of these, we've got 96 heads doing something. So let's learn more about what they do. And all of these heads operate in parallel, which is why we need to have the positional information encoded into the vectors. Now, each attention head, it focuses on a different syntactic and semantic aspect of the content. And so I'm going to step through this, and don't worry too much about this because we're going to come back around and talk about the essence of what's happening. But what happens is, for each word, there's going to be another 3 vectors. Query vector, that's focused on understanding the input. A key vector that's focused on figuring out the words that deserve most attention. And a value vector that kind of indicates its relevance to predicting the next word. So for each word, we've got these 3 vectors: Q, K, and V. And so there's one set of Q, K, and V vectors for each attention head. Now, these vectors are vectors of values that come from training. So you could kind of think of these as weights in a certain regard. And so what happens is, I misspoke. So we got the weights, and these vectors essentially come from multiplying the embedding by those weights. Okay, so that's step 1. We do some math here. Step 2, we calculate a score. So for each word, we calculate the score for the other words in the input sequence. So for thinking, we calculate the score for thinking. We calculate the score for machines, and so on for each word. Then for machines, we calculate a score for each word in the sequence as well. And the score is a dot product of the query vector for the current word and the key vector for the other word. So Q1 and K1, Q1 and K1, Q1 and K2, so Q1 and K2. So one of the really cool things about dot products is if you do the dot product of a vector with another vector that's really close to it, it's going to be a big number. But if you do it with a number that's far away with it, it's not. And so you can kind of start to see here a nice byproduct of this is that we get these dot products. Well, the similarity, the ones for relevant vectors, are the dot product is going to be really high. So we'll just kind of plant that in the back of our brains for a second. And so those numbers are going to be bigger than the other ones. So then we normalize the score, divide the scores by the square root of the dimension of the key vectors. So it gives us a bit more stability in the numbers. Then we pass it through a softmax, which basically normalizes the score so they're positive and add up to 1. So we're getting through to, some sort of probability-like score. Then what we do is we weight the value vectors. So the value vectors which we haven't been mentioning working with up until now. We've been working with the query and the key. So now we weight the value vectors and multiply them by the softmax score, which will drown out irrelevant words. And then we sum the weighted value vectors to produce the output of the self-attention layer. And so what we do is we basically sum it for each of the words in the sequence. And then what we do, because the next step is expecting a single matrix, we concatenate the outputs from all of these attention heads, multiply them by a weight that came from training, giving us the result Z. So it's a whole bunch of math, but let's talk about what in essence is happening under the covers here. So what's happening under the covers here is, remember I said that there are 96 layers, one on top of another, in this sequence. And within each layer, there are 96 attention heads. And each of these attention heads has a different set of weights associated with it that come from training. What essentially happens is these weights that come from training, they're set up to detect certain things. So for instance, on layer 8, head 11, we're trying to detect noun modifiers. And so we can see here, that the complicated modifies language. In the huge new modifies law. The modifies fight, and so on. The former applies to executive. This applies to time. So that's one of these heads among 96 in one of 96 layers. Another of them identifies prepositions. So the weights have come through training, and they're designed, when you run it through that math we just described, to essentially identify prepositions. Now, they don't always get it perfect, but they get it right enough times where we produce pretty reliable results. And so this is kind of, it's interesting, especially at the scale we're doing this. We're doing it, as I said, 96 of these by 96. Now, the earlier layers are identifying relatively simple things. They're doing things like, identifying where prepositions attend to, what word they're related to. They do things like, identifying synonyms for words. They do it, replacing those prepositions with some meaningful representation of what they're attending to. But then as you go further up the layers, they're starting to deal with not just these single word associations, they're dealing with broader concepts. And so and those concepts get more and more complex the higher up it goes through these layers. So let me switch over here. There's another visualization I linked to here where you can start to play around with this. This is an interactive tool. It's linked to from that slide. And what you can do is you could actually put whatever sentence you want in here. You can change the sentence. And what you can do is you can go and you can have a look at so it is a relatively simple system. It's got 12 layers, and it's got, I think it's got actually how many? 2, 4, 6, 8, 10, 12 heads. So it's got 12 layers and 12 heads as opposed to 96 and 96. And what you can do is you can see for each layer, you can choose a layer, and then you can choose a head. These colors are the heads. And so if I double click, I can choose a head. And you can start choosing individual heads, and you can kind of see what they're doing, what kind of connections they're making. Now, what some people have done is they've gone and they've tried to research this and kind of figure out what each head is doing. And that's what's happened with the paper that's linked to on this page. So if you click through to this paper, it will talk about what different heads are doing. So high-level summary here is what's happening is we're starting to understand the relationships of the words to one another. Okay. So now that we're understanding how the words attend to one another, let's talk about the next step in the process. It goes into a feed-forward neural network. So I mentioned earlier that this neural network, it only goes in one direction. It doesn't come back. So it just goes forward. It's a type of neural network. During training, when this is set up to train the system, the feed forward, essentially it's storing the knowledge it learns from all that training material. During inference, when there's a prompt, what it does is it uses that information it's learned during training to predict the next word. Okay, so it's a neural network. You've probably seen diagrams like this at some stage. There's an input layer to a neural network, there's an output layer to a neural network, and there's a whole bunch of hidden layers in between. And so we understand what neural networks do, but we don't fully understand how they operate. But we've empirically found that they do well with certain types of challenges like this. They're good at generalizing learnings from training sets, whether those learnings come from language or images. But given their vast size, explicitly training each step, it's impossible. So we haven't quite figured out the laws that allow us to fully understand how they operate. But we know they do a pretty good job. That being said, there has recently been a modest breakthrough in starting to understand how they work. A company I've mentioned a couple of times called Anthropic. What they've done is they've said, okay, you know what? If we trace these individual neurons and what's happening in them, you just can't wrap your head around it. We can't grasp what's going on. So what instead they're doing is they're looking at groups of neurons and they're working at it at that level, and they're starting to detect that actually there is discernible activity that's happening in groups of neurons. So we'll see where that research goes, but it is quite promising in potentially helping us understand the how. Okay, so we're dealing with a neural network here. So we got all these neurons. They're all storing some level of information. But very importantly, it's the weights between these neurons that hold a lot of the understanding of the system. Now, little step back, neural network, it's this vast network of nodes, but it's kind of beautiful in the fact that you send numbers in, and there's essentially a function that, helps this information propagate through the neurons all the way through the system. And it's quite simple. So if we assume that any one of these neurons has a set of inputs, X1, X2, X3, and there are weights for the connection to those previous inputs, W1, W2, W3. Well, essentially, there's a formula for calculating the value of that next neuron, and it's a function of the inputs, the weights, and a bias. There are a number of these functions that have been used. They're actually quite simple functions. The current flavor of the month for systems like this is a function that essentially is 0 until it gets to positive numbers, and then it's essentially a linear projection from there. But to give you an idea of the size of this neural network, I did a little bit of reverse engineering, and ChatGPT has about 105 billion weights. So it's a huge neural network. I don't know exactly how the neural network is configured. I don't know how many layers there are and how many nodes in each layer. But I do know from a little bit of reverse engineering based on information that's out there that there are about 105 billion weights in this network. So in other words, connections.
Conor, so just wondering on the terminology on that bullet, is that fast forward or feed forward weights?
Oh, feed forward. Thank you. Typo. Yeah. I include a link here where somebody has done a really good analysis of the math around these feed forward neural nets, which is where I ended up deriving that 105 billion number from. Okay, so we've got this big network. There's a whole bunch of math happening as we go through it. It's pretty straightforward math. We've empirically found that this math results in the capturing of knowledge for different types of challenges. Not sure exactly how that is, but we found it is, and that's great. So recent research has looked at these feed-forward layers, and it started to notice some patterns in there. And this is not the Anthropic research I was mentioning recently, but it's some other research. And what they've found is that for systems like this, that the key vectors that we mentioned earlier end up becoming pattern detectors in the input. So they will identify patterns in the input. And so there are some examples here. And so that's kind of interesting. They've also found that the value vectors help predict the next word, which is their intention. So that's good that they do that. But there are some examples that they've found that demonstrate that, and they go into the details of how they've been able to identify that from the neural network. But anyway, what I want to convey from this is that essentially every time we're going through each layer. So remember I said that we've got this architecture, we've got an attention step in the architecture, we've got a feed forward step in the architecture, and that attention step has 96 heads. Each of those heads goes up into its own feed forward network. And then this is layered, stacked on top of each other, one after another, 96 times. And so what in essence happens is each layer, we're building more and more understanding. So very simple conceptualization is, hey, let's say we've got a sentence, John wants his bank to cash thee. Well, it will go through one layer and maybe we'll, identify verbs. It'll go through another layer and it will start to disambiguate his and bank, and so on through the layers. And as it goes further up through the layers, it's doing higher and higher level conceptual associations. And so coming out at the other end of this, what we have is we've got a really good understanding of the prompt. So that's all that's coming out at the other end of this left part of the architecture. A tremendous understanding of the prompt that's coming into the system. Okay, now I want to mention that each word vector has 12,000, well, it's actually 12,288 values. And there is a hidden layer of about 50,000 neurons. So that means there's about 1.2 billion weight calculations happening in one layer. And then that happens 96 times. So we're talking about approximately 100 billion operations. And it does this every time through. So the reason I mention this is I just want to reinforce how many operations are happening every time this is just trying to understand the input and generate one word. So about 100 billion operations for every. So now you can start to maybe get a feel for why operating these systems, for why it's so expensive for OpenAI to provide this service. Because every time you're doing a prompt, you're getting back paragraphs of text in a response. Well, it's tremendous number of operations for each word in that paragraph.
Where are these operations physically done because of the speed? Are they distributed to be accomplished?
Yeah. So the question is, where are these operations physically done? So they are done within GPUs. Now, GPUs are not like typical CPUs. CPUs are quite flexible in the types of workloads that they can execute. A GPU is very focused on the kinds of math that we're talking about here. And a GPU has got a much more focused purpose. And as a result, tends to have supporting chipsets for doing these kinds of math super quickly in memory. And so it's happening in these super efficient processing units. And in your case, they're happening up in the cloud.
There are multiple units that handle each problem.
Yeah. So I can't recall off the top of my head now how many GPUs are involved in, for instance, the training of these sets, but it's a tremendous number. Here, I just wanted to capture some of the equations that essentially represent this architecture. And the reason I wanted to do this, so here at the bottom, we've got the equations for the positional encoding. Here in the middle, we've got the equation for the multi-head attention. And here at the top, we've got the equation for the feed-forward network. The reason I wanted to do that is, again, I want to reinforce, there's no working with words under the covers here. It's all math. And that's why so many people say that, hey, all we've built here is just some sort of statistical processing capability for the English language. To which you could argue, that's a reasonable thing to say. Where things get interesting is the fact that we have, via these numbers, captured interesting information and relationships. And so this is kind of moving back to last week's sessions where we started to talk about understanding and reasoning, which are built up in those layers. So it's not just a statistical processing engine for determining the next word. There's a bit more going on here. These numbers are starting to capture relationships between the other numbers, which happen to represent words, and concepts. And some of these concepts can be quite abstract. So it's doing an interesting job here. Okay, so that's essentially what I wanted to cover. I wasn't sure whether to break this down into, but let me do this. So technically, this is called an encoder-decoder architecture. The part on the left is the encoder, and the part on the right is the decoder. In very simple terms, you could consider the encoder to be what understands the prompt. You could consider the decoder to be what generates the next word in the response. And once you understand the prompt, there's no need to do that operation again. So in other words, the numbers that are coming out of understanding the prompt get locked. And you just do the decoder part of generating word after word after word. That's a way of thinking about this. I'm taking a little bit of a liberty there because actually everything happens in same time steps, but conceptually that's what's happening. Okay, time for some more questions.
First question, you're talking about a feed forward analysis here. And my understanding was that, I think it's Timothy Hinton that came up with a feed backward
Yes.
type of approach, which really opens some things up in this large language model or in the AI system.
Yeah.
Am I correct? And what did that do?
Yes, you are correct. So there is a paper that's currently undergoing peer review, as I understand it, from Hinton that talks about essentially the ability to go back and forward. So it's early days yet. And even as Hinton says, it's promising for certain types of situations. So bottom line is early days yet, but yes, we're probably going, if you're to step back and look at the big picture, I think the likelihood is, number one, systems like this that are monolithic systems addressing all challenges thrown at it the same way are probably going to evolve into systems where you've got specialist engines for dealing with special types of situations, I suspect. So for instance, this is really not good with math. So for instance, I could imagine a specialist engine for dealing with math. And I could also imagine specialist engines for dealing with different types of interactions that perhaps leverage some of these forward-backward capabilities that are currently being researched.
You're talking about ChatGPT here, but of course I guess it was last week, you had that wonderful picture of the Minuteman sitting out in the woods. And of course, so the idea of an image output, it's not putting out words, it's putting out elements of some, it's a little more abstract, fluid, whatever. Any sort of answer to how that is?
Yep. So the question is, hey, we're seeing what's working with words. What about working with images? Okay, so the answer there has changed very recently. The current state of the art is to use a technique known as diffusion, which was not the case up to a few years ago. So these systems have changed significantly in recent years. The way diffusion works, so first of all, we're using the same architectures here, but the way diffusion works is, during training, we start with an image. So we've got an image. We generate random noise. Just so imagine back in the old days when you had the TV and there was no signal coming through, it was all hazy noise. So you got random noise. You apply that noise to the image in increments. So let's say 10%, 20%, 30%, 40%, 50%. As you're adding more noise, the image becomes less distinct. It's very fuzzy. What's happening there is the system starts to learn through that process how to do the reverse, how to go from noise to an image. Okay, that's one part of it. Another part of it is, so there's an image part to it and there's a language part to it, because the prompt, you're going to handle language. So the system also learns to associate these concepts in language with elements of the picture. Mm-hmm. And so the combination of the two, it's kind of this reverse engineering. So if you look at the image generators now, what you'll see is, you'll see it actually starts off kind of blurry and it starts to become clearer and clearer and clearer. And what it does is, as it's becoming clearer, it's looking at the language elements you've requested and it's adding those to the image as it's adding those positioning, and then it just incrementally keeps making it better based on this, you know, adding addition of noise that has occurred over, you know, millions and billions of images that's been trained on. So that's a very short description, but same architecture with more stuff thrown in.
Logic systems of math is so complete, and the errors can be wrong. Are there logic systems that can use even Boolean to just try to sort out what's correct?
So the question is, are there logic systems?
They're just in the wrong numbers.
Yeah.
Or wrong answers, and why it gets there, and can it train itself to detect those?
Yeah. So the question is around, you know, it's handling of math. So in part 1, I mentioned that it would become clear in part 3 why it's not as good at math. Well, it's because of the way it's operating here. It doesn't have separate logic for processing math.
So when it gets incongruous information, does its head explode? What happens? It just waits one more than the other and say good luck.
Yeah.
Comes back with 42.
It's a good luck.
Yeah. And
Science means good luck.
yeah, so it's interesting. So like what happens with math problems is you're going to state them using, you're going to type them out. It's going to go through those layers, and it's essentially going to, you know, start off with, you know, simple associations, or, you know, in the content, but as it gets higher, it's actually going to start to do some of the math, not based upon mathematical operations, but based upon what it's been trained on. So that higher level conceptual stuff that in those upper layers, it's going to start to maintain a hidden state that captures these higher level concepts that it's identifying, and it passes on that hidden state over to the decoder. And so it is trying to figure it out, but it's not trying to figure it out in how we might think it's going to do math. It's trying to figure it out given how it's been trained. So yeah, it is trying to do it, but not using math.
Follow-up questions at this point. My understanding is that all of this is based on neural networks in the AI, broad AI system. I read recently that there are other approaches to this. For example, using formal logic. Now, math is based on formal logic.
Yeah.
But this is starting out with formal logic per se, to try to get to the same point. Do you have any comments to make on that?
So I'm not aware. Oh, sorry. The question is around some materials that are talking about using formal logic for math, and you know, new
ChatGPT or any of these kinds of large language models.
Yeah, so I'm not aware of that, which is not to say it's not the case. I'm a hobbyist rather than an expert. So
sure, you've taken us on a very deep and interesting dive of the generative part of AI, but you can observe that AI can take a specific set of text and break it down.
Yeah.
You can give it a sentence and say, diagram the sentence. What are the parts of speech? Spits out all the the results flawlessly, or give it a larger text and summarize this text. Is that functionality part of what you've described today? It's not generated, but it's breaking down.
Yeah, so in that case, what's happening is that's being learned outside of this architecture. So in part 2, we talked about the training of the system, and there were 3 phases. There was this part here, the transformer architecture, where it picks up, it starts to understand more and more about the content it's trained on. Then there was a second phase, which is human-led, which was where you train the system for the tasks you want it to perform. And for the most part, that was a human generating a prompt and a human generating an ideal response. And so in there will have been, I don't know, let's say a few thousand instances of the system being asked to summarize a particular piece of content. And then a human will have provided an exemplary instance of that summary. And so what will happen is the system is implicitly learning how to summarize stuff from those examples. So that part is actually part of its human trained.
But how does that apply to something like a New York Times article for today? I say summarize it.
Yeah.
So that's not part of the training, right? It's
Yeah.
just written.
Yeah. So what happens is using, let's say, several thousand examples of summarizing, it will identify that you start off with a general sentence or a general paragraph with the essence of what's happening. And then it will identify that you'll have picked out the 3 main points and had a paragraph on each of those. And so it learns the essence of that structure. And then it starts applying that structure to when it's asked to summarize.
Thank you.
Yeah.
John, that's you, right? Is that you or is that somebody else?
No.
Okay, I'm sorry. So John Howard asked, how are the indices of various vectors computed? They need to align to compute dot products.
Those vectors are, so if I understand what's being asked correctly, those vectors are determined at training time, the values of the weights for them.
I'm not interested in the values. I'm interested in the indexes.
So is this the right slide, John?
This is an appropriate slide. So we have here, for example, in embedding, you've got 4 elements. Obviously, it's a much larger number, right? You said something like 12,000. What maps against that the product that you're going to use that input as a dot product? What is it you multiply that's also got 12,000 elements in it?
Yeah. So what happens is, so the output here of the attention step is not necessarily that matrix from the embedding.
Mm-hmm.
It's essentially it's a weighted average. Actually, you know what? I've got another slide that might help explain it conceptually at a higher level. This one here. So again, we're imagining that the numbers have 4 values in the embedding. And what we're doing is we are taking the resulting weighting for each of the words. And then we're essentially coming out with weighted averages. So what's happening is it's the word "the" is going to actually be very highly correlated with "the." The words "the dog" will be somewhat correlated, and the words "the" and "ran" will end up being less so. So what we're trying to do is we're trying to identify relationships between words, and we're trying to do it across the entire body. Actually, let's see if there's a better.
So I understand. We've got 2 words. They've each got their element in the embedding. They're going to be the same length. Those 2 vectors, because all the embedding vectors are the same length.
Yeah.
But why? How do you know what the 5,000 or the 2,000 or 250th element of that vector is? How do you compute the index, not the value?
Oh, so the I'm not sure I fully understand the question, but so the embedding, the values in there, we don't have a good conceptual understanding of what value is being represented by the numbers at any index in
Right.
there. But what we found is that when we've trained the system to generate these vectors using these types of approaches, we found that the numbers so the resulting vectors tend to group similar terms in the same space, so they'll be close to one another. We've also found that the relationships between the vectors are actually respected by the math, but we don't have a good handle on, what the number at index 250 represents, or for that matter, 10,021.
Okay, thank you.
Yep, sure.
There's a fundamental gap here between reality and perceived reality, which shows up in all these things. I mean, even just the simple, as I was saying in the question I had in the chat about if you're typing something into Gmail and it's anticipating or correcting what you've typed, it's based on this large corpus, which may or may not have any real strong relationship with the corpus it should be connected to, which is what you are doing in the way you interpret things. So, the jargon gets lost in the thing if we're looking at the public as a whole, for instance. You don't catch the more significant stuff because the probabilities are very low that this particular usage will occur.
Yeah, that's a reasonable point, Ted.
It's obvious that the human brain is not doing things this way because we don't have any way, even if we're very, very efficient in each neuron, to have every one of our neurons functioning at the same time. We have a small number that are doing a particular task. And so these networks are obviously being pruned dynamically in the human brain, which is not happening in these more sort of static structures. And you can think of it just simply in terms of one word. For example, if I mention the word plasma to a lot of people, the average person has heard about plasma in the context of human blood. But if I mention plasma in the context of fusion, it basically sort of abstracts out a whole bunch of things, and the person who's adept in understanding the fusion concept of the word plasma has heard of the other one, but they've pruned away all the noise of that part of the system and gone directly into the science of electromagnetics and charged particles and things of that nature. Somehow or other, these systems have to either learn how to do that or they die because of just the sheer magnitude of things. There just aren't going to be enough processing elements and enough power to run them and things like that.